We solve for impulse mathematically. One thing that you're going to really want to focus on is impulse graphically. I have seen several AP questions asking you to solve for impulse graphically. So this is something that you need to know and you really need to understand. Finding impulse graphically is simply area of a force versus time graph. That's it. So to find impulse graphically, you are taking the area of a graph that's giving you force versus time. If this is a triangle, then pretty simple. Area is 1/2 base times height. So your impulse equals area. So it would be 1/2 F delta T. If you have graphs of different shapes, then you just take the area of those shapes. If you have graphs that are a combination of shapes, then you just break them down and add them together. So looking for impulse graphically, it is the area of a force versus time graph. Once you know that, then you can set impulse equal to what you also know it is, the average force, delta T, or the change in momentum, so M delta V. So graphically, we're using this part, but once we use the graph, then we can use the impulse momentum theorem. I'm going to do 2 examples. The second one's a little bit tougher, so I'll do the first one, just showing you simply how to apply impulse graphically, and then the second one, which again is a little bit tougher. So first, a shot putter throws a 7.2 kilogram shot put. The force exerted on the shot put by the thrower is shown below. Assuming the shot put starts from rest, what is the velocity of it after it is thrown? And then part B, what is the average force exerted on the shot put by the thrower? So first thing we want to do is use the graph to figure out the area. That will give us the impulse. So impulse equals 1/2. My base, we're going from 0 to 0.5, so this would be times 0.5 seconds, times the height, 600 newtons. This equals 150 newton seconds. So part A, we're looking for the velocity of the shot put after it is thrown. We know that impulse equals mass times change in velocity. So impulse over mass equals V final minus V initial, starts from rest. So V final is just equal to the impulse over the mass, 150 newton seconds over 7.2 kilograms equals V final. So 150 divided by 7.2, we get 20.83, keeps on going, meters per second for the final velocity. So V final is about equal to 21 meters per second. Okay, now for part B. Wants to know the average force exerted on the shot put. We know that impulse equals the average force delta T. We already know impulse, we already know time. So impulse over my time will give me my average force, 150 newton seconds over 0.5 seconds equals the average force, 150 divided by 1/2, 300 newtons is the average force. So this was a simpler example of how to use impulse graphically. Let's do the harder one. A 46 kilogram boulder is traveling at 12 meters per second after rolling down a hill. It collides with 2 small trees. The force acting on the boulder for each collision is shown in the graph below. This should actually be to the right. Calculate the speed of the boulder after the first collision, which is after 0.2 seconds if you look at the graph. And then after the collision with the second tree, the boulder is traveling at 2 meters per second in the same direction as its initial velocity. We want to know the maximum force. Okay, so for this one, I'm going to draw a diagram. We have 2 trees. And then we have the boulder. Hits the first tree, hits the second tree, and then keeps moving. Okay, this is easier if I just break it into part 1 and part 2. So we'll look at part A separately, and then we'll look at part B, and I'll just list a separate given and find. So given part 1, so this is the collision with the first tree. That's part 1. We know that the initial velocity is 12 meters per second, that the mass is 46 kilograms, and that the time is 0.2 seconds. And we're looking for the final velocity after it leaves that tree. So from the graph, this is a triangle. We can figure out the impulse for part 1. So impulse 1 just equals 1/2 base times height. So this is 1/2 times 0.2 seconds times 2,000 newtons. This is going to give us 200 newtons. But what we have to be careful of here, if you look at the picture, the boulder is traveling to the right. It's going to collide with the tree. The tree is providing an impulse on the boulder in the opposite direction that it's moving. The graph isn't going to show us that because it's only showing us the absolute value of the force, and it's just the way I drew my diagram. So because the boulder moves to the right, the impulse acting on it is to the left. My impulse has to be negative. So now for part A, we're looking for the speed after the first collision. We know that impulse equals m delta v. So impulse over mass equals v final minus v initial. Impulse over mass plus v initial equals my v final. This negative will matter because it'll mess you up if you don't put it in. My impulse is negative 200, this should be Newton seconds. Newton seconds over the mass of 46 kilograms plus 12 meters per second equaling v final. And this comes out to 7.65, keeps on going, meters per second. So my final velocity for part 1 is about equal to 7.7 meters per second. Okay, so now let's list a separate given and find for part 2. For part 2, my initial velocity is going to be the final velocity we just found from part 1. So that's going to equal my unrounded 7.65, keeps on going, meters per second. It tells us that the final velocity is 2 meters per second. And by looking at the graph, we can see that the time is equal to 0.15 seconds. And here we're looking for the maximum force. So just sliding up real quick to the graph. We have a triangle. We know that impulse for 2 is going to be equal to 1/2 F max T. We know time. We can figure out impulse because we have enough information. The only thing left to find will be F max. So part B. Impulse equals 1/2 F max T. Again, that's from the graph. This is also going to equal mass times change in velocity. Rearranging, F max will equal 2m v final minus v initial over t. And once again, this impulse has to be negative because it's acting in the opposite direction that the boulder's moving. So this equals negative 2 times 46 kilograms times my v final, 2 meters per second, minus my v initial, 7.65, keeps on going, meters per second, over the time, 0.15 seconds. This will come out to 3466.6, keeps on going newtons. So my maximum force is about equal to 3,500 newtons. I promise you will mess up if you forget to put a negative if your impulse is acting in the opposite direction of the motion. So make sure you're reading the problem, make sure you're drawing a diagram, and make sure you're figuring out the direction of everything. Otherwise, you will mess up and your numbers will be wrong. We'll do more practice with this tomorrow, but it is an important concept that you're knowing how to use these graphs to figure out impulse and then to apply it with the impulse momentum theorem that F delta T equals M delta V.